So, welcome back again, students. Let's calculate one example. That example will tell me the effect of temperature on equilibrium conversion. And so we'll calculate this example, but this is a very lengthy example. We'll not calculate whole. What I'm saying is that a certain step we neglect, certain things are directly I'm giving to you. By this is the equation, using equation we can solve it. But I will tell you how this equation comes. But I'm not deriving whole, but finally, like rate constant is depend on by this equation it's depend on temperature. The equilibrium conversion is depend on by this way, it's depend on this temperature. So by this way we can solve it. Because if we solve it, then it becomes a very lengthy. And we'll use the Excel, and using Excel we calculate the values, and then we finally draw a graph using the Excel. Okay, so let's calculate one example. That example will tell me once the reaction temperature is increases, conversion is decreasing. That is the things that I would like to tell. So let's calculate one example. Example like determine the equilibrium conversion. Determine equilibrium conversion for following elementary reaction. For the following elementary reaction between 273 Kelvin in bracket 0 degrees Celsius and 373 Kelvin. It means 100 degrees Celsius. So A gives R, at 298 Kelvin, delta G is equal to minus 14130 joule per mole. Delta HR is equal to delta HRT at 298 Kelvin will be the minus 75 300 joule per mole. Heat capacity CPA is equal to CPR is equal to constant. We have to plot XAE versus temperature graph. Determine, construct, or draw XAE versus temperature. Okay. So let's calculate this graph. We have to construct equilibrium conversion versus temperature. Okay. So solution. Delta G is delta G at 298 Kelvin will be the minus RT ln K at 298 Kelvin. So K at 298 Kelvin will be the exponential minus delta G divided by RT. So exponential minus plus is 141.139 divided by 8.314 multiplied by 298. So we'll get the value of K at 298 is equal to 300. Now at 298 Kelvin. So we have to calculate now the value of rate constant K at 300 at different temperature because we require from 298 Kelvin to it's from different temperature from 0 degree to 100 degree. So we require different K value. So one standard temperature K is we determined, but another K is at different temperature. So we use the ln K at different temperature divided by K at 298 Kelvin is equal to minus delta HR divided by R 1 minus T2 minus 1 divided by 298 Kelvin. Then, okay. If I rearrange this, I'm directly written down the equation. I will put delta HR value, R value, T2 value, K value, and finally I'm writing down the equation. K is equal to. I'm finally I will not write down the whole step. Just I'm writing down the steps. Finally, I just only rearrange the equation after putting the value. You rearrange the equation, and finally I am getting exponential K is equal to exponential 75,300 divided by RT minus 24.7. So now we find out the different value of K once I put down the different value of T and different value of R. Then okay. So now we'll get a value of K at different temperature. We can get the value of K. This is the function of temperature T. Now we have to find out the equilibrium conversion. How to find out the equilibrium conversion? That is the using this equation. A gives R and R gives A. Okay. So we can write down rate equation using this one. dCr divided by dt is equal to minus dCA divided by dt is equal to K1CA minus K to CR. Then now we convert here. We can find out CR is equal to CR0 multiplied by XA we can find out CR is equal to CR0 at XA, and we can say so once we do this, then we can finally we can get the equilibrium conversion XAE at XA is equal to XAE at dCA divided by dt is equal to 0. So finally I can get the equilibrium conversion equation. I just not write down the whole points. Just I'm decreasing some steps. I can get the XAE having a relationship with constant like this. Equilibrium constant at certain temperature plus 1. So what we get the equilibrium constant with certain temperature we put here, and then we can get a XAE. So now then what we take, then we have to draw one table. So drawing one table like temperature in degree centigrade, temperature in Kelvin, then rate constant K value at certain temperature, and then XAE. Then XAE versus temperature, we draw a graph, and then XAE versus Celsius will draw a graph, and we can get it. So now we use this equation, both equation, to generate a equilibrium conversion graph. We'll use this one equation, and we'll use another equation. To find out the equilibrium conversion. Okay, so let me use the Excel, and using Excel we can generate a conversion versus equilibrium graph. Okay, so we have a one-sided temperature in Celsius. Another, we have a temperature at Kelvin. Then we have a rate constant K, and we have a XAE. Then okay, temperature at Celsius from 0 degree. We require a 10-10 difference. So 0, 10, 20 up to we take 110. We can also go further. Let's take 150. So is equal to 0 plus 273. So we can get from up to now we can drag this one. And okay. Now equilibrium K will be find it out. Okay, is equal to exponential and 75,300 divided by 8.314 multiply by this one. This and we finish this bracket here and we'll finish this bracket here minus 24.7. Now we'll finish this bracket. If I take, let me take whether I'm getting correct answer or not. It's 4797.59. Okay. So if I drag this one, I'm getting a different value of K value. Okay. Now I'm getting a XAE value. XAE value we can get this one K this one divided by this value plus okay 0.99. Okay, so if I drag this one, so it's XAE versus T graph we have to draw. XAE versus T graph. You see the graph. XAE you see the value, you see the graph. Once the temperature is increases, equilibrium conversion is decreasing. You see it. So it means that if I do the temperature at nearly 150 degree, what I am saying, the conversion is equal to zero. If I maintain the temperature like 0 to like I'm getting this 92 percentage at 60 degree temperature. So once I decrease the temperature, I'm getting the conversion highest for the exothermic reaction. So to decrease the temperature in exothermic reactions, we get the equilibrium conversion. So by this way, this graph will be done. I will try to generate this graph. This like this way, endothermic graph is also created, but it's starting from this one and ending to this one. It's like this one. Okay. So let me okay this point and this graph. I will do it later, but this way will do it. So now next theory will be the graphical procedure. Next theory will be the graphical procedure. So let's go for the next theory, temperature and pressure effect within the graphical graph. Graphical procedure, general graphical design procedure. New topic, general graphical design procedure. Okay. So in previous one, we have only two-dimensional graph will be there. What are the two-dimensional graph? Rate rate of reaction versus concentration, or rate of reaction versus conversion. In previous one, we have only one graph. The graph is between the rate of reaction versus concentration or rate of reaction versus conversion. But at the time, why only one graph will be there? Because at the time we say that we have a isothermal condition. It means the temperature is not changed with respect to reaction. But here temperature is also changes. So we have three parameters. We have to draw three-dimensional graph. We have to draw 3D graph. So 3D graph is between the rate of reaction, concentration, or conversion. So both are same. Using conversion we can calculate concentration, and using concentration we can calculate conversion. And now the new parameter will be the temperature. So we also include it. So we have to draw a 3D graph, rate of reaction, concentration, and temperature one hand. But to understand this 3D graph and to draw this 3D graph is not possible. It means it's very difficult to understand. So what we have to do? We have to draw a 2D graph. We can draw a 2D graph. What we have to draw? We have to draw a 2D graph. So 2D graph, we have to draw this three graph for 2D graph. one graph will be the one will be the constant, and then two parameters we take. For example, one here we calculate consider parameter r constant r. It means the rate of reaction constant. So we draw a graph, uh, concentration versus temperature. So concentration versus temperature. So we take one rate of reaction at one rate of reaction, what is the temperature and what is this concentration? At another rate of reaction, what will be the temperature? That rate of reaction, temperature is changes, what is the concentration? At rate of reaction, temperature is changes, what will be the concentration? So if we take one rate of reaction and if we take different temperature, we can get a different value of concentration, and maybe we get a graph like this. That will be the for R1, one rate of reaction, and then we take a different rate of reaction, and once we increase the rate of reaction, we get a R2 value. So one rate of constant rate of reaction, if we change that value of temperature, we can get different value of concentration. But here rate constant is fixed. Now another one will be the constant concentration. So once we take a constant concentration, at that time we'll draw a graph. Rate of reaction versus temperature. So if we take one concentration and then we can change the temperature, we can get a different value of concentration. So generally at one concentration, graph like this, another concentration graph like this. Just we take an arbitrary things, we don't have fixed one. Then now the third things we take temperature as a constant. Constant temperature. Then finally we can draw a graph. For example, get one here the rate of reaction versus concentration. So one temperature may be graph like this, another temperature may be graph like this. So two here T1, here T2. So we have a three graphs. So up to this we have only 2D graph because temperature is not varying with reaction. But now here temperature is also changes. So what we have to draw 3D graph for rate of reaction, concentration, temperature. To draw and to understand the 3D graph is very difficult. So what we have to do, we have to make one parameter will be the constant, and then we draw a 2D graph. So in first graph, rate constant will be the R rate of reaction will be the concentration. So we see the effect of temperature on concentration. Second graph, concentration will be the fixed. So we change the temperature and we see the what is the effect of rate of reaction. And third graph, we take a temperature constant and then we see effect of concentration on rate of reaction. Here in all these three, the first graph is useful to find out the conversion, to find out the volume of reactor. And out of these three graphs, the first graph, constant rate of reaction versus concentration versus temperature, it will be the very useful to find out the volume of reactor. So so we can convert concentration into the conversion, and we will use this graph to make a to make another graph, and that graph will help me to calculate volume of reaction. So we'll use graph between the conversion versus temperature. We can calculate concentration into the conversion and conversion into the temperature, and where rate of reactions are constant. So there are three graphs. One graph for irreversible reaction, another two graph. Let me first draw this graph. So once zeroid conversion to 100% conversion and with different temperature. So let's take our first rate of reaction. If one will be there, then I am getting the graph like this. I am getting the graph like this. I am getting the graph like this. So at R is equal to 1, R is equal to 10, and R is equal to 100. And so irreversible conversion versus temperature with different rate of reaction. Now for this is the irreversible reaction. For reversible reaction, we have two graphs. Endothermic reaction and exothermic reaction. For the equilibrium conversion, XA1, temperature. For the reversible, exothermic, reversible, endothermic. Okay? Here is a 1, here is a 1. If reversible exothermic is there, then this graph will be followed like this, and reversible exothermic will be the graph like this. If endothermic will be there, then graph is like this. So here one rate R is equal to 1, R is equal to 10, R is equal to 100. And if this graph will be there, then R is equal to 0, R is equal to 1, R is equal to 10, and R is equal to 100. So this type of graphs will be occur. Now we'll use this graph to make a volume of reactor. So now we stop here. Next class, what we'll do, we'll use this graph to find out the volume of a reactor for the non-isothermal condition. So we'll use this graph, conversion versus temperature, and rate of reaction will be the constant. So we'll use this graph to find out the volume of a reactor in next class. So you write down your enrollment number and then you can leave the meeting. Next 11:55 class, what we'll do, we'll first take a practical, and then we take a small practical, and then what we'll do, we'll revision of the mid-sem 2. We'll solve some of the MCQs. We'll do MCQ practice. Then so now you write down your enrollment number and then you can leave the meeting. I will solve your queries in next class regarding the mid-sem, and we also do the practical, and I will give also your answer if you have any query. Then so at 11:55 we'll meet mid-sem revision, and we'll also do the experiment. आता purity, we are not much deal within the reversible reactions. So last two graph is not much affect to us. Will not consider much reversible reactions. Will consider majorly irreversible reactions. So these are the reversible reactions with exothermic and endothermic. This not much effect to us because we are very less reversible reactions are there. Now we will join next class meeting and we'll meet at 11:55. I end meeting here for all of you.